Okay, so first I'd like to welcome everybody here. Okay. First thing I've got to address is a couple of safety items, which is, should there be an emergency?
It's okay.
We'll get outside the exits here and at the entrance, and we'll go into the parking lot, yeah? Bathrooms, ladies and gents down there, the tip is, gents is the first one and the ladies is the second one, because it's really difficult to not that I have never done. The third thing is, if you've got cell phones, if you can put them on silent or turn them off, that would be appreciated. I'd like to give a special thanks to Nini, Steve and Christine for taking the effort to organise this. Thank you. And I said that any guests that have got any questions about the Institute or are interested in joining, if they would speak to any of the committee members, that would be good. So committee members, just stick your hand up and might have something to speak to. So any of these people, if you're interested, can give you the details of contact numbers. Our next meeting is the 13th of November. It's engineering analysis and when litigation is likely. So this is a joint meeting with the Institute of Marine Engineers. Linda Singh, our friend over here, we attended one a few years ago, and I must say that it's really worthwhile going to, and it's really interesting to see what engineers can do and what they can't do. And with that, I'm going to hand over to Nimi.
You're all welcome to present today. I'm going to invite our speaker, Sean, to give us a very interesting prepared presentation which we're going to enjoy. And of course, it's a technology that is actually emerging. I'm sure we have questions. Of course, we have what we want to really see synergy between technology and also the problems, challenges we face in our operations. So I call on Steve.
Imagine knocking that over, right? Okay. Has anyone ever heard of us or Aquanaut or any of that crazy stuff before? How many people hate it? That's good. That's first. So thank you very much for inviting me to talk. It's always great to do these types of things. I have made a career out of being a tech evangelist. It is a terrible career. I do not recommend it. Especially if you want to do business in oil and gas and you say, I got this great new technology. You know, all you need to do is change the way you do business. And everybody's like, so today I'm going to talk to you about Aquanaut. And no?
Down there.
There we go. Come on, get a door mechanical. There we go. So, I'm going to talk to you about Aquanaut and introduce you to our little company of ragtag scientists and engineers. Talk about how we build things, which I think is really important in this industry. There's a difference in how a huge company builds something and how a really small company builds things, and the risk profile of doing that as a business and the risk that will introduce to your customers, the operators of the world. Use cases for this kind of technology. Immediately start defending our technology after we describe the use case, because you can look at it and say this is absolutely nuts. Once I'm done with defending it, then I can defend it some more when we have questions. Everybody has questions about these kind of things. My personal joy in life is answering them, and I'm not kidding. It's really, really fun. I just ask you have an open mind when you look at this kind of stuff, and put the burden on me to prove that what I said and what I showed is real and doable, right? So there we go. I'll get this one day. Here we go. Here's us. Our little company was founded in 2014. And it spun out of NASA's Dexterous Robotics Laboratory. So there's the principals from that lab said, okay, thank you, government service, making $30,000 a year with a few PhDs is never fun. And this technology, you can imagine, you've seen probably the Boston Dynamics things and all those really cool robots doing backflips, and this is the type of technology that's going to run our planet And so they spun out and said, maybe this is the type of tech that the world needs. Let's go focus on a problem. And that problem became subsea, right? And I'll describe that a little bit. But now, so that's just 4 guys in a garage in 2014. Fast forward to now, we're 70 people. 30% of the team is ex-NASA. The remainder, like myself, are coming from industry. I came from oil and gas in Silicon Valley. We have a lot of folks who are coming in from robotics companies like Boston Dynamics and all the normal companies that sort of just tour around. We are a venture capital company, so we raised $23 million to date. We have 2 strategic investors in the company, and probably surprises you. One is Transocean. Nobody really knows Transocean actually does corporate venture capital, and the other is Schlumberger. Schlumberger has been doing corporate venture capital for a while. They actually funded my previous company, Aquanaut, as well, so they're familiar in this space. We have 4 products. I'm going to talk to you about this one, but we actually launched 4 products, and we only have 1 office right now. That's in Webster, so it's actually close to NASA, where most people used to drive anyway. And so our team, average age is 27, which is absolutely ridiculous. If you walk, and this is the most fun thing, we had Subsea 7 in the office a few weeks ago, and the number 1 comment was, this does not look like an oil and gas services company, because there's women walking around with mohawks, and everybody's saying, these are actually a company-issued shoes. They say HMI on them, be jealous. You know, we don't have to play by the rules. We don't feel that way, right? Because we're pre-product in a lot of our products. We're in this space where we need to innovate, and that space is not a comfortable place to be. It's not the normal type of person that you've seen in the oil field that does this fundamental type of innovation. And so we don't care. Our dress code, our formal dress code policy is yes. That is what it is. It actually is 1 word. It's dress code yes. We don't care what you wear. We don't care what you do. Come to work, be great at what you do. That's the only rule. And because of that, we've been able to get some really cool talent. And you can see all the companies that come through there, and everybody's smiling in these pictures. Most of them aren't smiling most of the time. They just go to work and they sleep at the office. But that's another part of innovation. This is also a really cool thing to point out. You know, if you ask a lot of your engineers at work, what is your background? Primarily the background for us is in robotics. Nearly everyone at the company is a roboticist. Even the folks who are mechanical engineers, well, they call themselves roboticists. That's all they've ever done. That's all they've ever known. And that leads to essentially a common development framework for all of our products. There's this thread that goes in between everything. And it's because everyone comes from the same background. We all speak the same language. Even you might be electrical engineer, you might be mechanical, doesn't matter. We've all done these same types of projects. And so it's much easier to develop something very quickly. And speed is of the essence when you're at any startup, right? Because you essentially are just staring, they call it the runway, right? And you're staring at this thing and it's on fire. And at some point you're going to need to fly, and hopefully it's before the runway runs out, or else it's game over like 70% of startups. We have a little bit of a different background in robotics than the ocean. These are the robots we built. So, Robonaut, which is in the middle, was a joint partnership between NASA and GM. It's unique because it was the very first robot ever flown to the space station. And there is a really cool video of Robonaut shaking the hand of an astronaut. And the reason it's cool, one, it's cool, it's a robot shaking the hand of an astronaut. 2, there's no e-stop on that robot. If it freaked out, if there was a bug in the code, it would crush the hand of the astronaut and maybe punch a hole through the space station. Now think about the level of reliability and engineering you need to do to ensure you're not going to harm one of the United States' greatest assets. Because you want to talk about expensive people to the government, astronauts are very expensive people to the government. And you don't want to be the roboticists that were responsible for the space station returning to Earth a little too early. And so that development process How long would it take, you think, to get that into the space station, get past all that? 2 years? 6 months. 6 months from that machine to come together and fly to the space station. That is incredible, right? Past all of NASA's things, past all of Russians' things, back when we talked to them. And that technology stack, the way that team invents, that's what came over to Houston Mechatronics. I think that's critical when we think about oil and gas, because the stakes are equally as high. It's not a space station falling out of the sky, but we have all seen what can happen in just talking about it, a low probability, high consequence scenario. Project Valkyrie is on all the way to the right. I don't know what the answer is. I believe that's a dab. I'm not sure. But that was a bipedal robot that was engineered to basically be the astronaut before we were going to send people to Mars. As you've probably seen, different presidents want to do different things in space. And as soon as the next president gets in, it's like, oh, Mars was great, but let's go to the moon. And then everybody throws away all their work and goes back. That was an attempt to say, human beings aren't going to go to Mars, we're going to send a robot that's going to walk around on Mars. And then that became like, well, walking is stupid. We walk because we have to. But rolling is a way better idea. So why not just make, imagine that thing, which is super cool. They called it the Centaur. That is a geologist. So the idea is drive around on another planet and have that machine, which could then bend down, take rock cores, pick up rock samples, and then store them in the payload bay for analysis, right? All these robots share three things in common. The technology was all about mobile manipulation, which is something we don't do in oil and gas right now, right? Our manipulation of the world subseas with ROVs, and that's done with a teleoperation, right? You've got a human being on the other line with a high bandwidth, low latency link, and you're driving the vehicle. There's a ton of automation now in those machines. They're far more advanced than they used to be, but it's still teleoperation. We want to manipulate the world. Here, on the space station, there's about a 15-second delay because of ground-based networks, and it's not really just a time delay like it is to Mars, which I think is 25 minutes. Here, it's more of just an issue with networking because the government is really bad at it. And 15 seconds, imagine going like this and waiting 15 seconds for a robot arm to do that. You'll never be able to operate it. So you couldn't, which is why we focused on autonomous manipulation, which is a real key to do over-the-horizon work with any robot. From a data sharing perspective, right? In space, like in the bottom of the ocean, the way that you can send data to someone else without an extension cord is really, really terrible, right? In the ocean, we use acoustics. That's a really high latency, really low bandwidth system. It's essentially, a comms void environment. Now, the implication for the robot is you may not be able to hit the E-stop. So what happens if the robot freaks out and decides to punch something, or it encounters an off-nominal situation? What does it do? And that's really where the safety stack, that's the safety component. How do you make a machine safe around things, which was critical to astronaut shaking the hand of the robot. You're not going to do that unless you have a safety stack, which makes a whole bunch of sense to people, and you've proven and qualified. Lastly, the control. If we look at ROVs today, we have a whole bunch of cameras, we have teleoperation of the manipulators, and we do have some autonomous functions surrounding the management of the platform's orientation and stability, right? But largely, let's just meso or macro scale this, human beings are processing data when they are operating ROVs. So you're taking in an immense amount of data from your environment, and you're processing it, and you're making a decision on what to do. And therefore, there's a limited number of people, or rather there's a finite number of people required to operate an ROV. You can't really extrapolate it all that well. You can't have, say, robotics that turns correspondency. You can't have a 7-to-1 correspondency because the machine isn't automated enough. Now, in a shared control paradigm, you're asking the robot to do the data processing. And the human being is still doing the very important thing of making the call. So human beings were really terrible at processing data. I always tell the story, my wife hates it. I always tell her, I'm amazing at multitasking. I'm not amazing at multitasking. I'm terrible at it. My wife reminds me of that often. Human beings are terrible at multitasking. We really are. You can't take equal parts of your brain and divide them. We love to say we can. Robots are really good at it. So what we do, and the way we control these systems, is we let the robot do the thinking, process the data, send the human being information that is required to make a decision. Let the human being make the decision, i.e. turn that valve. That is a decision. And the decision to turn that valve, and here's all the safety stack of what happens when you turn it. How far can it go? What happens if you see it off and on? All these things. Human being makes that decision. The robot does the manipulation, right? In this example, the robot figures out how to reach out, grasp the valve, and turn it in a safe manner. That is incredibly complex to do, right? You don't see many examples of that in oil and gas. That's why I spent so much time on this slide. We could just be clicking through. This type of robotics is the underpinning of our autonomous manipulation strategy for Aquanaut. And I challenge anyone here to show me an example of that subsea today, right? And I think when we're talking about autonomous concepts, think about that as the underpinning of how we treat the world autonomously and we manipulate. So let's talk about Aquanaut. So today, you're familiar with the two types of robots in the ocean in oil and gas. Loop them into two, AUVs and ROVs. Autonomous underwater vehicle, torpedo things, and the ROV, which everybody knows about. AUVs are the world that I'm from. In an AUV, the strengths of this platform are I love them, right? It can travel at a very long distance, very efficiently, because it is in a torpedo form factor, right? So it is tuned to go a long, long way, very, very efficiently, burning on the order, that particular vehicle there will burn just prop, no sensors, except for what's needed for the vehicle to go. The thing only burns 20 watts. That's ridiculous. So that machine can host a great number of acoustic sensors and seabed mapping sensors. And its launch and recovery has been worked on since 1995. And it uses a smaller vessel than an ROV. So what it's great at, and what it's used in oil and gas, is for pre-site survey. It is the most efficient way in deep water to survey, period. It used to be deep tow, but then we needed another boat, and Thomas Chance from C&C said, why use the other boat? And cost was the reason, and BP made the choice and said, hey, let's try this technology. That's how AUVs came on in 1999. It is not the perfect tool for IMR, because it can't stop. They talk to the manufacturers and say, yeah, it can definitely stop. No, nothing that's a torpedo hull form factor can stop and maintain hydrodynamic stability all that well. In order to be very stable, it needs to continue moving. And so when it stops, it actually does a circle, in a very small circle, but it's still always moving. It doesn't also have anything on it to manipulate the world, right? So anything it does is non-contact, right? It's a non-contact sensor. There's these things, for an IMR example, CP measurement, right? In CP measurement, there's a non-contact CP method used in AUVs. The science is I think, quite objective. And the only reason that it exists is because, well, that thing moves at 4 knots for a day, no problem. An ROV is not moving at 4 knots. So economically, you want to use this thing, but it's not the right solution because it can't manipulate the world. It can find a bunch of things. It has a whole bunch of edge processing power, but it doesn't have the ability to do anything about what it found. ROVs, well, these things are amazing, right? They are the underwater workhorse of this industry. They are divers. They can be outfitted in any number of ways for missions, right? Bolt things onto it. You've met any ROV guys, they're the most resourceful people on the planet, right? With duct tape and a few zip ties, they can do anything. And that's because this machine is tailored for that. You need to be able to do a myriad of tasks with it. It's great for construction. It's great at station keeping. There's so many thrusters on it, and it has an unlimited power essentially because it's connected to the ship. So it has tons of power. They don't really even worry about it. And it has a decent manipulator on it, right? The manipulators are hydraulic, but people have gotten really, really good at using them. Any good ROV operator is worth his weight in gold. But they're, again, not perfect, right? Because it's really slow, goes half a knot, maybe not. It's the add-on architecture of it means that you're sacrificing data quality. My example is always Android phone versus iPhone. You load a whole bunch of garbage onto an Android phone and the phone will crash. You can't do that to an iPhone because they control the whole app ecosystem better. And it's much more of a tied-in ecosystem. ROVs are like the Android. AUVs are like the iPhone. And sometimes you put a sensor on an ROV that was never meant to go on it, and it just doesn't work right? Because it's not built to integrate everything. It's just built to hang stuff on, put some power there, send the data back up to the top. And in the military world, kind of hard to do work subsea very covertly with an ROV. The U.S. military does it. They use fishing boats. This is how great we are at covert activities. This is very public information. We monitor all of the cross-Atlantic cables because the Russians monitor them as well. And so we go down and we inspect them in places where I think, maybe the Russians kind of put something to listen to stuff. So we find a shrimp boat. We put an ROV topsides on a shrimp boat, and then we sail that damn thing into 6,000 meters of water. And we launch the ROV. It's like, oh, nobody will find us. It's just a shrimp boat. It's like, what the hell is a shrimp boat doing in 6,000 meters of water in the middle of the ocean? The Russians are not stupid.
There should be a drone.
So, from a position perspective, terrible thing. But there's no other choice, right? There's not another other choice. And with the magic of a Venn diagram and terrible colors, you'll see what is in the middle of these two things. What can move far, what can manipulate, we can. That is why we made Aquanaut. It has a cool color, and it certainly looks cool, but the reality is it's a utilitarian device. We had to make it look cool, or else IEEE would never cover it, and we didn't get any press coverage. Nobody would ever talk about it if it looked, we just painted it gray. But the reality of today's subsea environment is that there is not one good tool to do both things. And the customer, all the operators, they're asking for cost reductions. And how the hell are you going to reduce your costs down past the boat, right? You're just losing money is fantastic, but it's not sustainable. And so we created this type of technology. And I don't consider it an ROV plus an AUV. I consider it that weird centaur thing plus an AUV. Because the ROV would be saying, oh, I can teleoperate it. And certainly we teleoperate the vehicle, right? Even right now, we can teleoperate it. But the reality of achieving the vision of Aquanaut is that it needs to be able to do autonomous manipulation. And the framework of that does not exist in ROVs. So it's this NASA technology that the team worked on for almost 20 years, thrown into what is essentially commoditized engineering in autonomous technology today. Here are the different stages of transformation of Aquanaut. It is a real-life transformer. It is so cool. When you're next to it, it's way bigger than you think. No one has come to the office yet and said, man, this thing's way smaller than I thought. It is bigger than me. And when it's in its hydrodynamically efficient state, we call it essentially the AUV mode. It is an AUV. It's going around, it's collecting acoustic data, it's mapping the world. it has a whole, essentially a robotic brain on it, but it is optimized for efficient transit at slow velocity, because most survey velocities are 4 knots or less, right? The transformation process is 4 linear actuators that push the hulls apart. And you can see there's 2 trays. The arms are back in. And the arms come out, and then they are energized and they're ready to go. Some of the interesting things you'll see here, it's all electric. There's no hydraulics on the vehicle at all. It is built to be used without a boat. We're using a boat today, but the vision of this product, when it's finally done, is it's going to be vestless. And there's no teleoperation of it, right? So there's no high bandwidth teleoperation. We hit go, we give it objectives, it accomplishes those objectives. In AV mode, here's all the stuff that's on it. This is very common to other AVs in the industry. On the very front of the vehicle, it has a forward-looking sonar, a high-frequency forward-looking sonar. It's got a disparity mapping capability. So if you've ever seen robots like Johnny 5, and that first slide, Johnny 5 had 2 cameras. That was a disparity map, so it could use depth of field. And it's just a way to essentially map the environment the robot's in. It's optically based, though. The head unit, keep one another. The head unit rotates freely all the way around. So the imaging package inside of the head can actually rotate up and inspect the underside of hulls. It can inspect the inside of a giant pipeline. We did it so the vehicle can, separate payload capability from what the vehicle needs to be able to do. The vehicle needs to be able to map its surroundings. Part of making decisions is equipping the machine with enough capability to map its surroundings. And part of that is that rotating head. There's a novel acoustic communications array that we worked on with Woods Hole, and essentially it's just a way to reduce noise, right? Signal to noise reduction. And the way we talk to it, we do talk to it over a medium frequency acoustic modem. So 1990s dial-up and super high latency. So it's a big challenge when you're sharing information between the robot and the human being. Discuss how we fix that, or how we figure that out. In AV mode, there's 3 thrusters. There's a aft vertical thruster, which controls the pitch of the vehicle, and there are 2 main propulsion thrusters, which is your main thrust, and then some counterbalancing of roll. There's a mechanical scanning sonar that's very common on ROVs. Again, obstacle avoidance for the vehicle, so it can ensure it understands what's in its sphere of manipulation. And normal LED lights and radio systems and GPS and things like that. When it transforms into ROV form factor, we get a few more little toys to play with. 5 more thrusters come out. You have 2 additional verticals in the front of the vehicle. There are 2 at the side. You can see those, the lateral systems. Those are pretty neat. It also shows, or it demonstrates one of the unique design principles we had. There's a whole, if you've ever seen the Michael Bay movies, there's like 1 million moving parts in a transformer. That is not going to be reliable, ever. And part of our challenge here is how the hell are we going to make this reliable? As a, keep it simple, stupid thing, right? So keeping it simple means let's make as few moving pieces as we can. And that basically means that those those lateral thrusters and the tailpiece have a mechanical linkage to the hull. And as the hull opens, the laterals move out and the tail moves up so that we're thrusting on CG to make the vehicle more stable in this configuration. And because it's just a mechanical linkage, we don't have to deal with additional actuators to make all these things move. The arms are 8 degrees of freedom, which are way higher than a standard ROV has. And the reason is that you, in a normal ROV arm, you don't want that many actuators because the human being has to coordinate all that movement. Or you have to have a crazy system to coordinate it for you. Our goal here is Cartesian end effector navigation, which essentially means touch that space. That's the command you give the robot. Pick something out, right click, touch this. In order to achieve that, the robot needs to navigate its end effector. And in order to do that, you give it as many joints as possible to achieve the desired position. And quite literally, we have bounds only for the joint position. Sometimes it picks this really weird position in order to manipulate correctly. And it's simply because we're letting the robot brain do what robots do great, make all these instantaneous decisions. Say, how should I modify my arm to best kinematically achieve this desired location? There's this square chess piece, like the Optimus Prime sort of windows. That's a really neat sensor. It's a three-dimensional structured light. And so if you're familiar with LiDAR, which is just thousands and thousands, millions of points with one light burst, this is different. We're the first company ever to move one of these subsea. And what it does and why it's really unique is its refresh rate is significantly higher than any subsea LiDARs, period. It's an order of magnitude faster, right? We didn't do it for payload, we did it for the robot. Because the robot needs to see its world, and it sees that through this point cloud. Now, a common LiDAR on any ROV or AUV, it needs platform motion or actuation in order to move. It's just a line, and you move that line up and down or sideways on the structure in order to image it. So you always need platform motion, or you need another actuator in order to get data. This thing doesn't need that. It's essentially like a camera. It just takes pictures of the world, but it's LiDAR. The advantage to the robot is now it can track its own manipulators in super high frequency. So not only are you saying the inertial navigation and coordination of all these degrees of freedom happens in the robot's brain, you're double checking all those calculations with real world measurements from a fixed frame here to the end effector. Now, the advantage on the payload side, that particular sensor was used to check pitting and corrosion on pipelines. It has a 0.05 millimeter precision. The thing is insane. And so you can check the condition of a structure that you are trying to manipulate down to the corrosion level. And it's a value add for us because we did it for the robot, but the reality is that the payload benefit is there because the customer always wants to know the condition of their asset. So super cool sensor. There's 2 batteries on the vehicle. At present, we only have 16 kilowatt hours of power, which is enough to run your house for a few days, or this for a day. The options are coming, and we're switching battery chemistries. You'll find a lot of robot people are always talking about batteries because you have a finite energy supply. So there's a new chemistry coming out. Aluminum seawater batteries are becoming popular again. Kids from Stanford figured it out, and were promptly acquired by L3, big defense contractor. We're working with them on a new type of battery, which essentially has an order of magnitude more energy than LiPos. And if you're in the battery world, that's insane. We didn't see this, no one saw this coming. And it is a really interesting reaction. It's not one of those types of reactions that can run off. With the old fuel cell reactions, use potassium hydroxide and heavy water. I remember very distinctly having my coveralls burnt through by one of them. It was not a pleasant experience. And this particular new type of battery doesn't have that. The reactant is actually seawater, so it doesn't even start working until you put it in the ocean. It's a really cool system. We're evaluating it now in the DoD space for the company. It is an all-electric robot. There are some hydraulic components. It's hydraulic oil. We're using oil for pressure compensation in the volumes so that we don't have to have 1 atmosphere housings everywhere on the robot. We use EAL, which is, yes sir?
Sorry, just sorry to interrupt. How big is the seawater battery that you mentioned?
It comes in a variety of sizes. This will tell you how big they are. I saw one in Tupperware that was about this big, and that was, it linearly scales. So its relationship to LiPo linearly scales with size. So for whatever volume you had in LiPo, it's an order of magnitude more energy density. The open water power. If you want to give them a Google, you'll figure they have a few data examples now. So it's open water power. The EAL, it's Biomax, it's biodegradable oil, it's cooking oil. That's what we use. It's not under pressure, right? Because it's not actual hydraulic. I'm not using it in a hydraulic system. It's just there for pressure compensation when hydrostatic flow is high in the system. I think that's it. Yeah, the head still rotates and pitches so that it can see the road. So that's a whole bunch of stuff. Its size. So Aquanaut, and this is one of the older slides we had. It used to be yellow, and then we figured what's in it. There's a good story between the color of Aquanaut is a Ferrari color, Pantone 172C. You ask any person at HMI what our company color is, they'll tell you Pantone 172C because it is just drilled in everybody's head. That color Porsche bought from Ferrari for $40 million, which is just nonsense. We bought it from Pantone for $72. So Aquanaut is 1,300 kilograms. It is not small, right? It's 3.5 meters long in its AUV form factor before the arms are out front, right? In Superman form factor, called Superman, where we put the hull up and then we put the arms forward and we drive. In Superman form factor, it's a 5.5 meter long system. So it is not small. In ROV form factor, you'll see we're about the same size as an Oceaneering Enovis vehicle. So that was done by design. We couldn't be any bigger than your normal work class ROV, and you don't want to be any smaller because then you're not going to be robust enough to actually handle the conditions for the work. Ooh. All right, our development speed. Most people, when they come to our office a few months apart, are really confused because we are very fortunate to move. I call it ludicrous speed, and it feels really fast. And here's an example of this. May of 2018, that was Aquanaut. We announced it at OTC. We said, yeah, Aquanaut's great. We had a set of arms. That was its first test right before OTC. We actually cut the trade show video at 11 p.m. the night before OTC opened. That was what we had. 1 year later, we put the vehicle totally done, put the vehicle in the NASA NBL facility. Again, well, this time we learned lessons, and there was a whole day before OTC opened, and then we recorded all this video for the trade show loop. In the span of a day, those are the NBL divers, they're a necessity. So you'll see it doing ROV stuff. It's tethered, right? The tether's not for power, it's for communications. Just try using acoustics in the NBL facility, and you'll see it's even worse than the deep ocean. And you see, oh my God, it actually did transform. And what you don't see is everyone freaking out at the pool deck because you're like, oh my God, this works. Because that fundamental innovation, you're never sure, right? You're never sure if what you did is actually going to work. And so here we're moving it around a little bit. We're checking the station keeping ability. This is, of course, really sped up. We're moving nice and slow in a very measured way because you don't want to ruin the thing you just spent a few $1 million to build, right? And then you'll see here we're going to transform at some point. We're going to bring both arms out, and you see this is doing the head sort of moving around. We're checking sort of the checkout function of the vehicle, and the head moves around. We check out, is it all the way good, lock to lock? And the vehicle will bring its arms out, and it'll become a machine. And there it is. It's real. Now that was May, this is September. It's working. So from May, the very first time we put it in the tank, to September, it's doing AUV things. And it's doing ROV things in the field. And we're following it around like idiots. That was actually at Lake Travis, which was a fun experience. Wakeboarders do not care about robots. We just like, no, don't. And they're like, all right, bro. And they come up, and then they see him just come like straight in over the robot, and then this pucker moment. Like, what did I do? Why did I do this? And this is the span of just over 1.5 years, and we built something people told us we couldn't build. And there's other videos and stuff we can show you. It does autonomous manipulation, and it navigates in free space. This is not by accident, and it is very, very hard to do, but it's just the development pace we have is rapid, and that's very much a startup thing, right? Because this is a high failure rate environment, and it's make or break, and we know it. And so the effort of all of these people, and a lot of people sleep at the office when things are real bad, because we have to, right? And the pace is, I think, exciting, certainly for me, to do this transformational work. So, we'll talk about Aquanaut. That's the vehicle. This is what we're going to do with it. Is everybody familiar with residency? Hear that term thrown around? Hybrid residency, things like that. So today, the future of IMR is residency. Someone proclaimed that, said, awesome. What is that? And so we compared what we want to do versus what residency is. And we came to the conclusion that residency is a stepping stone, right? It's the next place we are going to go, but it isn't the final destination. And if we look at a few metrics here, response time. Well, the things in the residency, it's in there, it's in the field. Response time is going to be amazing. So that's great for the customer. Communications, right? That's a robot problem, but that's also a way to de-risk it. High bandwidth comms, because it's going to be cabled back to surface, and then you're going to have your over-the-horizon haul, and that's going to be great. Power requirements. You don't care with a resident system because you're going to recharge it, right? As Aquanaut, keep calling it Statoil, Aquanaut has their underwater inspection drone, and they are giving every company that came over to us, they gave us their templates, and this is what you're going to have to recharge in the field. You better be able to use it or you won't work for us. So, Sean, thank you. This is terrible. But it's free. It's basically a free Tesla supercharger. Who's going to say no to power? And you don't have to have a long duration battery because you can recharge. Reliability. This is where I think subsea residency falls apart. Think about what we need to do to engineer a tree and put that tree subsea for 25 or 30 years. There is a ton of effort done to put that tree down there. You got to do the same level of engineering for a robot, except it's got way more parts. And we haven't been building them for 30 years. So, in my opinion, and it is my opinion only, right? I think you're looking for perfection in robotics. And perfection you will not find in robotics. And you will not find perfection in the ocean. Put anything in the ocean, as any one of these ships or any one of you can attest, the ocean is going to find a way to beat it. It's just a matter of time. And think about the economics of a resident field. If you're, say, Oceaneering, who's really pioneering the idea of residency. If you're Oceaneering, one time, call a boat out to go fix your robot one time, and you've ruined the economics of residency. Because now you had to use your expensive boat, had to come to the site, maintain your robot, and the customer wants, really low price, because no boat anymore. I want a really low price. The other part where it falls apart, or the other metric where it falls apart in my opinion, is I always use the plumber analogy. You have an old house, and the pipes leak. You call a plumber. They come out, they fix your pipes, and then they leave. And this subsea residency is stay in your house. They live with you. Nobody likes that, right? That's way more expensive. And think about it though, if this is the next step, and the industry is asking all the service companies to take risk to make the next step, they're not going to eat their own lunch. They're not going to violate their business model. Their business model today is vessel-based, right? Days sold per boat, and that's how they report it to the IMarEST. That's how everybody sees the world, is by vessel days sold. You essentially have the same thing here, because you have to keep a resident system there 365. And if it's there 365, they're charging you for it every single day, which means you're paying for it. This is why we decided to use what we call hybrid residency. Now, I had a name for it, which wasn't popular in the office. Light asset, low logistics, distributed service architecture model. LOLISM. that doesn't exactly roll off the tongue. Our CTO had a different name, Uber for subsea. Right? This is what we're getting at. Got all these assets in the Gulf of Mexico. Some are fixed, some are moving, but they're all there. They're all topside. We're going to put a bunch of other stuff in the Gulf of Mexico. You're going to call the robot, and it's going to transit to you, and it's going to do work. That way, you're not paying for mob, you're not paying for demob, you're not paying for the robot to be there all the time. You're just paying for it when it's there, just like Uber.
Uber doesn't make money.
That's a fair point. I'll show you how we will. Everyone looks at that slide, and the very first reaction is, you're an idiot or you're crazy, right? And maybe both. And I don't disagree with either statement. But let me show you how we're going to buy down this risk and actually make some cash. How do we solve this equation? It's our burden to solve, right? If we don't make money, then the company goes out of business. Oh well. There's three big problems that people see with this type of model for us, right? Logistics. How are you going to manage the logistics of that network, right? And how are you going to do that cost effectively? That makes no sense to anybody. Is the market ever going to want this, right? Everybody says yes, they want it. But will the market ever accept something like this where it's really hands-off? Great example is when we first showed this to Chevron, they said, well, it's kind of like if every Uber car had a wrench, and then you called them out to West Texas to go wrench on something and then go back all autonomously. And I would never do that. So the gentleman saying that, I said, okay, have a great day. Comms. How are you going to talk to it? How are you going to command it? How are you going to control the risk of the asset being so close to all of these structures? That's a big, big problem. And it boils down to communications. And how are you going to organize communications with the robot? All of those three things go into perceived risk. The perceived risk of that kind of solution is super high. Super high. And we recognize that. So the very first statement is, that Uber thing is not happening tomorrow. We're not that dumb. Right? We understand the pace of this industry, and we understand that we cannot just roll out with a crazy idea and say, oh, well, this is available, you're going to save a whole bunch of money, you just need to take about 2x the risk you had before. Then again, that's me looking for a job. So we understand it's going to be a long time, and we're going to stage the technology in, right? Just because I engineered it to work over the horizon doesn't mean it can't work with an extension cord plugged into it, right? Conventionally, to help prove the technology actually does work. Because when you have high bandwidth communications with it, and you're still doing things autonomously, you can still hit the e-stop, you can still have a human being intervene. But it's a way to buy down risk, right? So we know that this is a long return period play. And that residency may be the thing, right? That may be what we do first, because the industry's starting to accept it. And residency is a great problem for us, because we have way more comms than we thought. We have way, way higher bandwidth than we thought, so it's much easier for the platform to do it. But when we control Aquanaut, we talked about this shared control. The safety stack of Aquanaut is pretty interesting. And it starts with the technology we put in the robot, and it ends with the human being, right? So you take your normal hazard stuff, take your normal risk profile, and you program that into the robot. And then the really unique part, and we just found out from the government, we cannot talk about it anymore. So it's actually ITAR now. They ruled on this. We invented a new way to compress data. A few people in the industry have seen it, because the government didn't tell us it was ITAR until very recently. But essentially, we found a way to do 75,001 compression, which is nuts. No one can do that. And so the government's like, wow, that's great. We're taking that. So we can license it from them, but largely I think that the amazingness of that compression will stay with the United States military. So we're working on a different set of compression routines. They're maybe slightly worse, But there's nothing, in my book, 50,000 to 1, 75,000 to 1 is not going to make a difference. The reality is the machine is imaging its world, right? It's imaging its world with point cloud data and cameras and all these high bandwidth things. We need to find a way for that to get back. And in the early days, it's going to be the extension cord, or it's going to be something called free space optics, which is a really high bandwidth system that a lot of operators are now thinking about installing on structures, right? And in that way, you can control the vehicle very easily through these systems, and you don't need all these compression things. On the compression side, though, what we have is the ability to take a 20, 30 megabyte point cloud and transmit bytes of data, and then reconstruct it onshore with 5% or less loss, which is truly impressive morphologically, because you really can't do that with anything else. Important to note, we are not relying on video. That's a paradigm people can't get their heads around, right? ROVs, you rely on video because everything happens with a human being who wants that high frequency information. And we're saying, well, the robot's smart now, so let's get to a point where we don't need video, because a robot doesn't need video. And I'm not going to be right next to it. That's not today again. That's I think, a 5-year play for us. But in the short term, video is the key, right? Now I'll show you here when I talk about safety stacks. Here's the robot autonomously turning a valve. So it's finding the valve, it's repositioning, and it does it kind of slow, right? I blanked out some sensor that we had on it, because you see the arm foam's not on the arm. We're gonna close, we don't close, rather. We do the turn, and you'll see we told it to turn it too far. And watch what happens with the arm. See how the arm starts counter-rotating? That's what we call force torque control. That's a super, super important thing to have. You don't see any RVs that have it today. And what it is the robot understands how much force it is imparting onto the world. And in the safety stack, we say, don't turn this, in this instance, don't impart more force than X. Because the valve's stuck. Don't just snap the valve stem off. Right? It's essential. Right? One of the key parts about sharing control of the robot is equipping it with the instrumentation it needs to see the world, to figure out what it's doing to the world. And that's force torque. When it reaches that maximum force threshold, it senses that and says, oh no, I can't impart over X newtons. That's not going to happen. So to gracefully stop doing that, it's starting to counterwind its other joints. That's where you see that arm motion where it goes this way. And once it counterwinds the joints, it unloads that force, then it stops the action. And the programmed action is to release whatever it's doing and back away, call home. That is the program action for, say, an over-torque event. Right, there's one example of how we can put the safety stack in there, deal with bad comms and an over-the-horizon e-stop, and still not harm equipment. There's advantages. Again, a lot of times we talk about a robot and making a choice for the robot technologically that ends up being really good for payload. So when we do a hot stab, we take the same technology, and what it allows us to do is misalign the hot stab, which is in ROV work is a pain. We misalign it and watch the arm move a lot like when it goes to reinsert that hot stab. The arm moves a lot like a human arm, where the human arm would, if you were misaligned like this, the human arm, you would move your elbow in and apply force. So see here, it goes down and over and then puts the hot stab. We didn't direct it to do anything. So put the hot stab back in the hot stab receptor. That's it. But because it has all the sensing on the arms, it says, okay, yeah, the forces aren't aligned correctly on the axis. I need to reorient the arms, push it in. So super useful piece of technology that both keeps the asset safe and helps the robot do its job better. Logistics. How are you going to get things to site? Question we are asked all the time. There's several ways to do this. The primary way, and the way that we are likely going to demo next year, so we're all about showing things. People love talking, so we think talk is cheap, right? So we're going to actually go do this, and we actually found an operator who's willing to let us do it. What we have here in this web map, all those little text box are locations of transocean drilling rigs. They're all over the world, in every major oil epicenter. Transocean is a very important stakeholder in Houston Mechatronics, right? They have a CVC play with us. They have offered us to put Aquanauts on all their drill rigs, right? There's value add there. Aquanaut can do a lot of the ROV type work. And if we want to, we can just go that way and go do something, right? And so you start looking like, well, what the hell does that even mean? So here is the Gulf of Mexico, the current location by marine traffic of every Transocean asset that is currently working, or at least reporting over AIS data. And overlaying on that are working areas for Aquanaut where we have acceptable communications and vehicle range. Notice we have a few hot spots in some areas that are actually pretty high revenue inside of the Gulf of Mexico. So we're not running machines out. We're not going to ask the machine to do a transit that it's not able to do. We're using what I call the lily pads, right? This is a lily pad strategy. There's all these lily pads in the ocean we have. The base case is that a drilling rig is a lily pad. Now the reality of that, super complex, right? If Transocean are working, we'll say BP, you're drilling a well for BP, are you allowed to launch another robot while you're drilling a well? We haven't come up that yet. The operator says maybe. Maybe's a good answer we get today, but those things need to be resolved. And so this is base case. Alternate case, we are currently working with three different vessel providers in the Gulf of Mexico that are running boats out all the time. And this is what we plan on doing. We're going to put our own launch and recovery system on these boats that are just pinned in, 4 little twist locks, 4 ISO locks, right? And we're going to pay them some money to keep those on there. I'm going to put a flat piece of plate on there when our stuff's not on, so they can still do their job. But when we need them, they're going to go pick stuff up for us. And they're going to go launch stuff. So that we're going to drop a little container on that boat. One of our staff, they're going to go out and launch and recover, because things happen in the ocean. It just happens, right? Perfection in robotics, we're not going to achieve it because the ocean won't allow it. So to account for that, we're going to have a roving asset network, which are these vessels of opportunity, which we have long-term contracts with. We're paying just a small sum of money just for the option to have our stuff on there. And then we can mobilize rapidly from, say, Fushan or Mobile. In the last piece of this puzzle is, and it's weird, if you've seen some of our marketing stuff, it says no vessel, no problem. Okay, sure, we'll work on the ocean and not on a boat. We're gonna have a boat, it's just gonna happen, right? If you work on the ocean, your stuff breaks, how do you get it on? And so once we reach capacity inside of here, right, inside of these areas, we have to have our own boat in case the whole fragile ecosystem we built falls. And at very early days, this ecosystem will be fragile. We know that. And so we have to account for that with a vessel that we have permanently mobilized, which is doing other stuff when it's not actually picking up Aquanauts, so that we can monetize it appropriately, so it's not just a drain on the company. So that's the logistics part, right? Really, really hopeful we get to demonstrate this in, say, Q2, Q3 next year. And that this will be literally launching from a drill rig, transiting 30 kilometers, doing something kind of money, which we feel is a 5-year play at minimum in the oil and gas world. If we were able to do that, turn and burn in oil and gas in 5 years, I'll eat one of the company issued shoes. It would be a miracle. So really great to see the customers are already starting to think forward. And say, is this crazy or is this real? I think that's kind of the flavor we got from them, but I'll take it anyway. Market, this is a huge, huge consideration. If the market doesn't adopt what you made, you go out of business. So we have 2 things we're doing, in the market and internally. In the market, there's a huge cost driver here, right? This is not an expensive service to operate, period. And in the beginning, it certainly will. Right? We're going to have to figure out robot problems, make things more reliable, tune the system. But we're a venture company, right? We're venture capital funded, so it's our job to make sure we can figure that out. The venture capital position is great. I don't have to wait for an operator to pay for something. I don't have to take money. We have not taken a single dollar from an operator to build Aquanaut. We built it on our own dime. Obviously, venture capital money, but we call it our own money because it's not free. You do have to give part of your company away for their cash. But that venture capital position allows us to aggressively invest R&D in an area we feel comfortable in and not have to wait for the industry to go there. So we can push the boundary of what we think is real today. And partnerships. Key for us going to market, it's like any small company, it's going to be partnerships. Who can we make that is a trusted name? Who can we make friends with that's trusted and go to market with them? And this progression of slowly walking the technology to its realistic bounds, right? It's like, oh, day 1, fiber optic tether. Day 2, no tether. Day 3, boats over here. Day 4, boats way over, right? Walking that through with a partner really bridges that trust gap that any operator will have with a small company like ours. Internally, when you do a moonshot, it's not a great idea as a business just to focus on the moonshot because you need to diversify a little bit. And I'll show you, by doing the moonshot, we created a whole bunch of really cool technology, which we're moving into its own vertical and just selling as a product. And focus. When you do diversify, now you have a focus problem. What do you focus on? And focusing staff in the right way. You think it's hard, say in 2012, is it hard to find an engineer? I think it's hard to find an engineer. Try to find a roboticist. And more importantly, try to find a roboticist that's born in the United States, which is a requirement from the military. Because it's really hard. We have maybe 2. And the rest are foreign born because the rest of the world has way better robotics programs than the United States does. And so focusing that talent in the right area is actually quite a decent administrative challenge. And so here's our product tree. Aquanaut is the thing. That's our moonshot. It's going to work. We're very comfortable with that. But we're not going to hedge that that's the only thing that's going to happen. The arms are really neat on Aquanaut. They have a lot of sensing. Their precision is really high, so we said, let's rip them off and make ROV arms. So we're going to do that. And we said, all right, well, ROVs don't want the same crazy stuff that we're doing. So let's make them, a little bit more realistic. It looks very much like a normal ROV arm. It's way easier to operate because it has all that autonomy built into it, but it's still teleoperated. It's just really automated. And it's all electric. Everybody's launching all these electric ROVs and have these little teeny tiny arms, and it's so cute, but they can't do anything. And if you look at all the electric ROVs today, SMD just came out with this beautiful ROV, and it has a hydraulic power pack on it to run the arms. That is foolish, straight up foolish. And the reality is nobody thinks you can build an electric arm that's strong. We did. Just yesterday, I witnessed a test. We pushed 14,000 pounds with one electric actuator that was this big. That's in there, 5 of them. That arm at full extension can hold 700 pounds out straight and do little twirlies, but that's electric. I just saw that. But that's just because we made Aquanaut, and we said, man, that's really cool tech. Let's peel that off in its own vertical. Our company can still survive. We can make money now while we're waiting for Aquanaut to mature. Same goes with the software that runs Aquanaut. We call it Commander. We're productizing Commander and some of the vision system. We call it HMI. See what I did there. And those two things are with the Olympic arm are going on a conventional ROV to make it smarter. Because ROVs could be smarter, and people accept some automation on ROV. And so we're going to be able to take in all this machine vision data, have the arm more point and click, so that we can get people used to these types of concepts on normal ROVs, so that it's less scary when Aquanaut comes to town and is doing it by itself and it's its own piece of hardware. And lastly, of course, like any company, we're selling things. We're actively in negotiation with a whole bunch of folks, and we're doing Department of Defense work. The comment about giving your position away, the government really likes things that can do stuff underwater without giving your service position away. And their risk tolerance is a little different than this market. Well, we think we can do that, and you're like, super great, here's my wallet. And then if you can't, then the wallet goes away. But the good part is, right now, we're in that great phase where they're giving us these challenges, and we're figuring out new ways to do work, and taking some of that technology and transferring it amongst this family. So, we can actually stay in business while we're waiting for the thing to mature. Very last thing. Disruption, right? I hate this term. I love this slide. We are a disruptive company. We are building disruptive technology. And in many ways, we're innovative. There's this line we always use, and this is straight out of our venture pitch deck, right? 12% of Fortune 500 companies are still in business. Everybody loves to say that. The reality is, what I like to think, I think of disruption this way, because this disruption is a dirty word. Disruption is, as a business, you get big enough so that one day you manage success. That's what you're amazing at managing. You manage the success of your company. But fundamental innovation is the management of failure. And as a big company, you forget how to manage failure because you've taken failure and kind of made sure you don't do it. You're only managing success, you're not managing failure. We manage failure. We're okay with it. Like where we are today in innovation, we have to be okay with it. As we progress, we'll hopefully be the same big old company that's like, oh, I remember when we used to screw up all the time too. We loved it. We called it an asset. But fundamental innovation is the management of failure. And I think we forget that in this industry because we're asking huge companies to innovate. And I don't see it. I don't see them coming out with crazy ideas that are innovative, that are pushing the industry forward. And there's a myriad of issues why. But my personal feeling is that fundamentally, big companies manage success, they don't manage failure. And you can't innovate without failure. And that's disruption to me. That's why we're seeing a lot of companies like us in this market today. So take questions. If you saw this video, I love this video. We cooked a turkey on Thanksgiving with flamethrowers attached to robot arms. One interesting fact about cooking turkeys that we did not know, because none of us can cook, that was not thawed. And apparently, thermodynamics is kind of a terrible thing. When you heat up a turkey with a flamethrower, it explodes at about 5 minutes. And that guy got hit in the face with a turkey leg. And the entire lab was covered in guts. And it took about 2 weeks to find all the pieces. It was disgusting. But it sure looks cool, right? So, sorry, I know I ran a little long. That's it. I know you've got questions if you think we're just too crazy for questions.
I have a question. So you're saying you have to manage the failures, right? When you are doing your prototype, what type of procedures would you use for understanding your weaknesses in your design?
Yeah, for sure.
So we in Subsea, we use API 17N. We do PRs, TUs, TRLs, Femicas. I wonder, from this design, which one would be the weakest design?
Okay, so the two questions. So we are.
Go ahead. You're going to answer her question?
Sorry?
You're going to answer her question, right?
Yes.
Okay. Now I have one answer.
Oh, okay. Femica, we do Femicas on everything. We hired a NASA engineer that did reliability on the space shuttle. We gave that person control 100% of our development and said, figure out how we're going to do quality assessment, quality assurance, and quality control, right? And so we use NASA's Femica process, and we have an iterative process that moves from nothing we do. We never do anything without doing sim first, right? So from a process level, we use NASA FAMICA, which is not API 17N, but it's the API equivalent of it.
Well, for subsea, we have specific requirements, but just wonder how you mix that with NASA would be interesting.
Yeah, I guess so. At present, we are on a equipment reliability, essentially for space flight. We use that process. The way we mitigate risk, or rather predict failure, is we use simulation for everything. Nothing happens on that robot prior to simulation.
So accelerated testing for each.
So, for instance, on that Olympic arm, the robot arm, that's been in simulation for 2 months now. And we've developed a control system for it for 2 months and been running a dynamic physics system for 2 months inside a sim, tuning the control system, figuring out what we want to do. Then we progress it onto a test bed. That test bed is, like a bunch of 80-20 and lifting weights and things like that. That finally gets out to real robot. Once the real robot happens, then we have an after-action review. We do failure mode analysis on it, and then we feed all of that back into that cycle once again.
So we have like levels of readiness.
Yeah,
so
the TRLs.
So for your product, you have TRLs.
So the
TRLs 5 or
API TRLs are different. We use the military ones.
We need to talk.
So the military ones were TRL 7, 8 on the military one. I think that's equivalent to a 4 or 5. Because we've done in water testing in like scenarios, and I think that's 5 on API. I was asked that question yesterday. I didn't have a good answer either. So we can look it up.
Because this is new technology, so we need certain stages to complete. But also wanted to know from your design what would be the weakest link.
Yeah.
So I know what would be.
So the weakest link by far is autonomous manipulation, right? Gracefully failing at that. Graceful failure is a very hard thing to do in robotics because it's essentially just coding, right? You've got to make sure your code is bulletproof. You've got there's a process a standard we follow. It's essentially ISO 9001 for code that. It's difficult to manage the risk of that code doing something you haven't seen, given how dynamic the environment the robot is in. And so figuring out how to do that with sim and figuring out what we need to qualify it with has been a challenge thus far, and I think will continue to be a challenge because the autonomous manipulation is sort of the unicorn thing.
One thing is the lab testing and one thing is
the actual dynamics, I mean, it's easy to do in sim, but putting it in the ocean is not cheap. You don't exactly get people like, turn the valve on that tree.
Yes.
No, won't happen. Yes, sir.
Well, it leads right into a very simple economic question instead of engineering. Who did the return on investment analysis for your venture capitalists?
Schwab.
Really?
Yeah.
Because that would seem to be a very interesting analysis.
There actually
there
are
had
some.
to be a whole bunch of, how would you call it, unforeseeable,
Yeah.
put it, roadblocks.
So the ROI is one thing. The risk associated with it's another, right? So I think that they understand it. We are very much a transparent company. You have to be. Well, you can hide stuff in oil and gas, but at one point you're going to put your stuff in the ocean. So we understand the risk of this development is high, which is why you see the product diversification, right? You put in new silos for things that people easier to buy, easier to make money. But the payout here is pretty high.
Well, it could be very, very high. That's why I was wondering who did the analysis.
Yep. No, we've actually we're going through it again. We just had another investment bank do the analysis again, and it has not changed. Well, I'm gonna call, but I don't believe it. I'll take it though. Yes.
You talked about the dynamic environment and how you can't predict everything. What happened? I know this might seem far out, but Like what happens if it gets attacked by a shark or
Yeah.
a squid or what?
Yeah.
Is it gonna fight back? Is it just gonna get crushed?
Hold on.
No. Put a heart with
I'm not going to show. Shark punch mode.
All right, well, that's what
So that was one of the early t-shirts. It does not have shark punch mode. Peter would be all over us. The reality is, we call it off nominal events, right? We're not going to know, period. So what we go is we go by platform dynamics. So we know that the dynamics of the platform, we should be rolling, pitching, yawing at a maximum band of this. If something outside of that happens, we have a behavior the robot can execute. We won't know it's a shark. Right? I mean, you can take a picture of it and send a picture to shore, and it's like, oh, it was a shark. That was a squid. But the reality is, if you look at what any wildlife or unknown event would do, it can be measured in the forces the robot is experiencing. And that may be an inertial force, like an acceleration. It may be a roll moment, yaw, whatever. But you always have inside the safety stack what the expected conditions should be. And then if they are outside of that, what we have right now, and it's not perfect by any means, what we have right now is the robot needs to stop what it's doing and move to a safe place. Same as a human being, right? You do a stop the job, get to safety. That is what the robot does. You're very right. The ocean's a dynamic place.
Watch out for the kraken.
Sorry?
Watch out for the kraken.
Yeah, I mean, if giant squid comes up and takes the thing down in the deep.
On the fishing net.
Sorry?
On the fishing net.
Yeah, exactly.
Oh, that's a good one. Yeah.
So the fishing net is an old AUV problem, and the vehicle is able to resolve ghost nets. Nets just left out there during its transit. It's able to see those with the variety of sonars it has, which are active during transit, so it can avoid them. Active fishing, though, let's say you're working in shallow water, the vehicle's aft turned to a net, somebody's dragging, always could happen. Our job in those scenarios, and this is where the economics come in, right? We feel the only way we have a chance at working is if we say the number one thing: don't hurt people. As a Moss laws, right? Don't hurt people. Don't hurt things. You're third. The robot's third. So as long as we don't hurt people and we don't hurt the infrastructure, then we're okay with it. Obviously, you lose a multi-million-dollar system, your insurance is not okay with it, nor are your investors. But it's a risk you have to take, certainly this early on.
Is there any impact on the marine life with the technology that you're using, like acoustics?
It's all low power. We did a marine acoustics analysis that you commonly have to do if you were to do a seismic survey in a marine protected area. So we did that for all the sensors on board. We are less than 160 decibel at the critical frequencies for marine life, and therefore no special conditions required. There is a lot of electrical energy in the water column, so it will attract sharks. All right, sharks love electrical energy. We've seen it. Wildlife is attracted to it, lights and stuff. Interesting thing is, we use lights as human beings. The robot doesn't need them. The robot's using other sensors, so we just don't turn them on if the human being doesn't need to actually manage the robot live, which will help with marine life. Yes.
So, in maybe slightly wrong, but with computing power, they talk about power doubling or MPX is, right?
Yeah.
Is there something equivalent with robotics?
It's not directly tied to Moore's law, but our ability to be self-sufficient is tied to Moore's law. So every year we do have twice the computing power in some instances. And so the phrase is edge computing. You've heard of that before. It just means that the robot's brain gets bigger. And so what we have on board the system is our electronics model is updated every 6 months. We are now on revision 4 of all the equipment on Aquanaut in 1 year. And most of that is computing power because we need to take advantage of every single teraflop we can in order to ensure the robot can process the data efficiently.
It's absolutely amazing. There's a professor in Tulane in Louisiana, Frank Tipler. You may come across him. I'll send you a link. He wrote about this 20 years ago.
Sure.
And most of his predictions are coming true. He says ultimately the robot or the artificial intelligence will surpass human intelligence, and it will include emotion.
Yeah.
So he's predicting this, and I keep thinking we're getting closer and closer to those points.
I don't want to see that day. I don't think that day
Not yet.
is going to end all that well for us.
They're not gonna pressure well the high.
No, I mean, we have to be
6,000.
very real about how dynamic these things can be, right? Market adoption is one thing, but the vehicle's ability to do dynamic things is going to be hampered for even for the next 5 years. But if it starts developing emotions, I'm out. You had, I'm sorry.
What about water depth limitations?
Right now, the current version, the very first version is 300 meters. The version coming online next year is 3,000.
3,000?
Yep. And then at the midway part through 2021, 6,000 meters.
Meters.
Yep, meters. Yes, sir.
So, this may be a more prosaic question, but so with the distributed model of logistics,
Yeah.
are they going to be drawing power and station keeping from support vessels when they're waiting to be distributed? Because when he mentioned the Kraken, one thing we run into is the Kraken eddy and how ROV, and when you've got these loop currents and stuff, how the ROVs can struggle to be able to be utilized in these high current environments. So you have a long-term model for managing power draw, the increased power draw, and the increased, running into high current settings?
Yes, sir. That's an excellent question. So the advantage of us, so let's address operating in high current environments first. We actually have like the best solution ever. We just transform into AUV, go deep, get underneath it, and work out that way. If you've got to work in it, you've got to work in it. But you can always get to your other form factor, hydrodynamically efficient, and get out of it, which is super cool. The more important question, how the hell are we going to have the power to do all of this? We consider, and again, residency, right? Keeping something under the ocean for a number of years is super hard. We don't want to do that. So we take the risk of going through the air-sea interface. So we have an autonomous launch and recovery system from the drill ship. Vehicle will home into its home. So it says, oh, yeah, this is my cage. I'm going to go in my cage. Cage comes up, vehicle stored out of the water. That's its connection back home. We can go work on it, we can go fly out and work on it much, much easier. We don't want it to spend a phenomenal amount of time in the water because that's a high risk for the technology.
And so the launch and recovery system is autonomous as well?
Yes, and it's actually, we're on that thing, LRS systems, right? You get 100 different revs on it. So we're on rev, I think, 106. That's not a lot. It's in the hundreds at this point. It's no slip ring. So it's a self-contained system because we want it to be able to use from vessels of opportunity. So if that vessel has a crane, for instance, we want to be able to just put this thing on there and dump it in and not worry about slip rings and special winches and stuff. So the vehicle homes to the docking interface, mates with it, and then it comes through the air-sea interface. It's pretty neat as it stands now, but we've only built it in small. We haven't built it at scale yet, so who knows if it actually, really will work.
So you don't anticipate having on location service personnel or a high manpower requirement from?
So certainly at the beginning, yes. The natural maturation of the technology, our desire is to have 7 Aquanauts for 1 operator. That would be more for management of an AUV task because the correspondency will have to go down in typical ROV tasks because you've got stuff to watch. And the customer may need to be next to you, like turn that valve, watch that, and tell me what's up so that I can stop you. That's going to ruin the correspondency stuff. But when the vehicles are just mapping the environment, 7-1.
And so your correspondency compared to having DOI-4 or something on station launching the ROV, full crew on the vessel.
Yep.
I mean,
So
that's where I see it coming.
currently our crew is 4 for 24-hour ops.
Okay, guys, I think we've got to wrap it up and let people get home.
Sorry.
No, I think everybody's very. I'll put it. Thank you. Right. So, thanks very much for everybody coming along and making the effort. I realise it's getting a bit late. I'd just like to present you with a certificate of appreciation. So, thank you very much.